All right, guys, chapter 4. This is about solutions, and it's about stoichiometry. Again, two things that you probably don't like independently, but when you put them together, it makes it a little more challenging. So we need to know what a solution is, and we need to know what stoichiometry is, and then we definitely need to know what they are together. So what are solutions? That's A number 1. What are they? They are mixtures. What are mixtures? What are mixtures? A combination of substances put together. Now, there are two types of mixtures. What are the two types of mixtures? Very good. So we've got homogeneous, which you probably can't see that green pen. So let's change it to orange. So you've got homogeneous or homogeneous and then heterogeneous. Those are the two different types of solutions. Here is a trick question. Are all solutions in the, quote, liquidy state? No. Can solutions be solid or gas? Yes. Are you breathing in a solution of gas right now? You absolutely are. Because it's the only thing you're breathing in oxygen. No, it's not. But we know a mixture is more than one thing. Okay? Are we breathing in more than one thing? Yes, so it is a solution, right? But why do we have issues with saying solutions can be gases or solutions can be solids? We see them when we hear solution, we hear and see and think liquid or aqueous, which is the correct terminology, because there is a difference. But solutions are anything that are two or more substances. Which type of mixture are we breathing in? Homogeneous or heterogeneous? Why homogeneous? It looks the same. That's the difference, okay? We know homo and we know hetero means same or different, but what does it mean in the state of a solution? It's the physical appearance. So if you want to write that underneath this bottom part, it's the physical appearance. How many of you have granite countertops in your house? Okay? Do they look the same throughout? No, you can see the speckles of the different colors, right? So you know that granite is a little bit different. Now here's the weird part. Blood. It looks the same. However, can you force it to look different? How? Spin it. What's that thing called? Very good, a centrifuge. What does it split it into, you biology people? 4? Plasma. Okay, so you've got red blood cell, white blood cells, and then the plasma, which contains the platelets. What's the buffy white coat? It's really 3 layers. Am I crazy? It's 3. The buffy white coat is the fluid, the plasma, and the platelets. So it all is in one. But you can draw the fluid out of it. So again, that's all about biology. Now, again, but here's the key. Can it be separated by physical means? That's what makes it a solution. Can you separate it physically? Now, we're also going to talk about this. What is a physical mean of separation? And I do want you to write some of these down. And this pen is working so slow. I'm going to change this. All right, so write this on the left. Distillation, crystallization, and filter. These are the 3 ways, as of right now, actually, and one more. Chromatography. Those are the 4 ways, and there are a few more that I can think of right now off the top of my head that we will talk about independently. Distillation. When would you use distillation? Okay? What are you doing? Distilling it. What else could you use distillation for? Did I misspell that? I'd put an extra T in there. Okay, very good. Alcohol. Okay? Crystallization. What? Actually, you're right. Meth. Crystallization is meth. Now, why would you want to crystallize something? Potentially. You're thinking of like solid crystal. Why would you want to crystallize something? Okay. If I take sugar water, how can I get the sugar out? Boil the water out. Eventually, when you begin to boil all the water out, what are those pieces of sugar molecules going to do? Crystallize. So that is crystallization. Okay? Filter. Obviously what? You separate the solids from the liquids. And then chromatography is a little bit different. Yes, ma'am. You pretty much heat the water. Crystallization is for hydrates. Really, it's for hydrates because you're trying to either A, get the water off of the crystal, or B, trying to get the crystals out of the solution. No. Okay. Filter is obvious. Chromatography is the separation of molecules based on their polarity. Okay, so let me give you an example of chromatography. Again, it's the separation of molecules based on their polarity. So I think I've talked about this before, hadn't I? Kinda. What you do is you take it and this is alcohol. Okay, and you take a piece of filter paper. Okay, and in that filter paper you take a Sharpie and you make a little dot. What is this alcohol going to do? It's going to run, and I'm going to use the run as the brown color. It's going to run through that black dot. Now, in art class, what is black? All colors. So what's going to happen is you're going to get, and I don't remember exactly which order it is because it's been so long since I've done it, but you're going to get the rainbow effect. So you're going to get red, and then you're going to get orange, then you're going to get yellow, you're going to get green, and then you're going to get blue, and then you're going to get violet. What did I skip? Indigo. It's now. There's no such thing as indigo. And it may be reversed, and I can't remember exactly which one it is. But what's going to happen is this alcohol is going to separate these molecules because every pigment, what is a pigment? A color, has different polarities based on the size, based on the shape of that molecule. So it's going to separate it out. So you can tell different substances in certain crystals based on their polarity. So that's what chromatography is. Pretty much, but the alcohol is going to run the colors, okay? Because what happens is alcohol is polar, and so it grabs onto polar molecules at different attractiveness levels. And so think about it: if something is attached with a string or a chain, which one could you pull farther? A chain. So does a chain represent a stronger bond? A stronger force or a weaker force? A stronger. So the stronger the attractive forces, what does that tell me about the distance you can pull it? The farther up it goes. So the higher up the molecule color moves, the stronger the intermolecular force that it has with the alcohol. I think blue runs the farthest. It's been forever since I've done it, but I think blue is. Okay? All right, so we started talking about this. Solute versus solvent. What is the solute? It gets dissolved, right? Okay, it is dissolved. This board's really slow today. All right, what is the solvent? It does the dissolving. What is the universal solvent? Water. Does that have to be water? No. Prime example, chromatography. What would be your solvent? The alcohol. Okay. Real quick, as a matter of fact, I actually want to show you this. So let me pause the video for just a second. Yes, sir. Okay, so this was from the actual test last year. This was question number 2, I think. And so what they did is this is an actual distillation lab setup that they had. So let me just kind of show you what it is. So let's start over here. Glass wool with ethanol. What is ethanol? It's an alcohol-based solution, right? Why is the glass wool in there? It's basically what they soaked it in. They soaked it in and just stuck it in the test tube, okay? Solid catalyst. What is the whole purpose of the catalyst? Make it react faster, right? What is this? Heat. What does heat do to alcohol? Vaporize. God, this board is painfully slow today. All right, it vaporizes. So what happens is that you got, what is alcohol mostly consisted of? Mostly water, right? With a few things bonded to it. So it's water and alcohol mixed together. So what's going to happen is it's going to come out of this test tube, and it's going to run down here, and then it's going to sit in this pail of water, okay? And then the alcohol, which has turned into what? A vapor. Vapor. To be more specific, it's turned into a vapor. It's going to go down through this water, through this tube, and bubble up. Okay? So, would this be able to determine exactly how much gas you had in that particular substance? Yes. So this is distillation. This is able to purify the ethene molecule from ethanol. Okay, so that is basically a distillation lab. So if you notice what it says may be prepared by the dehydration of ethanol. What does dehydration mean? You're pretty much boiling the water out of it. So when you take the water out of it, all you're left with is ethene. Remember, just a real quick talk about what does eth mean in organic? Meth, eth, prop, bute. So it's two, and then what? To what specifically? Nope. What is? And we're in organic. 2 carbons. And what does that tell me? All right, so I've got 2 carbons, and then ene ending tells me what? It's a double what? A double bond. So I got a double bond sitting here between these two things, right? So how many hydrogens would I have on each one? Why 2? Very good. Every carbon can have how many? 4, right? So this is the ethene molecule. I'm just kind of showing you some organic stuff just to say we've talked about it. So that is ethene molecule. Yes, sir. Um, no, not that I'm aware of. No. So again, and this is what it has. So it shows the ethanol. What is catalyst again? Makes it go faster, right? Boils into ethene and water. Now, why does ethene get separated from the water? What's going to happen as the water goes down this test tube and into the pail? What's the water going to do to the water? It's going to trap it in, right? Will the water continue up into this tube? No, it's basically going to make an intermolecular force with the other water molecules that are there, so it will not continue to travel. But will the ethene make a bond with the water? No. Here's something I need to ask you. Let me redraw the structure. Why would this structure not be pulled into the bucket of water? Not bonds. But what does that have to do with it? Kinda, in a way. Alright, what makes intermolecular forces occur? Polarity. This did not stick in the water. So what does that tell me about this thing? Very good, it is nonpolar. Now that you see the structure, can you tell that it's nonpolar? Where is all of the electrons, the heavy electron density sitting? Right there in the middle. So if I've got carbons pulling this way and carbons pulling this way, which end is going to win? Neither one of them. So do you agree you kind of, in a way, have something almost kind of like that going on? Even though that's not really true, but in essence, do you have any partial charges going on? So since this is nonpolar, will it mix with water? No. So if you're going back into looking at this, what are these bubbles? It's the ethene. That's why it doesn't stick in the water. If ethene were polar, would it be able to escape the water? No, because what would the water do? It would trap it in, right? It would form one of those forces. And again, we're going to get to these things. Delta H. Change in enthalpy, right? It's an energy value. Delta S is a new one we had never talked about. That is entropy. That is amount of disorder. So calculate the number of moles, blah, 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 blah. Due to the thermodynamic data supports its claim because the dehydration reaction is equilibrium costless. And we'll get into every bit of that. What? Yeah. Data is singular and plural. So it can be used. It sounds really weird, but it can be used as singular. It doesn't sound right, but it's always like that. Alright, so let's go back into this. And here's a little joke for you. Just a little solution here. I can't even see what that says. I just love hanging out with you, chloride. Hee hee, sodium. Oh no, that's water. What? Where? I'll never forget you. Do you get why this is... So they're in love, they're hanging out, they're great, they're wonderful, and then these big bad guys show up. What is water doing to this particular compound? Separating it. I like to refer to water, and I'm totally going to butcher this. Say it again. Spell it. Somebody look it up, because there's not two R's? Piranha. I hate this word. All right, Piranha. So you've heard this before. All right, so basically what happens, water has the ability, because here's the new buzzword, and you may have heard it, you may not have, but I do want you to write down, polarizability. That is a really big word. Polarizability is what? The ability to become polar. I get it, ha. But what does it mean? Okay, it is, in essence, it's how strong is the electromagnetic force of that molecule on something else. Do you have a lot of electrons? Do you have little electrons? The difference in electronegativity between hydrogen and oxygen is very little or very great. All right. The difference in electronegativity between hydrogen and oxygen is very little or very great? Very great. So does the water molecule have a high polarizability? Yes, which means things it come in contact with can also be flipped into becoming polar. So when you have sodium and chloride, does that say sodium or does that say lithium? Sodium, I can't read it. So when sodium and chloride are bonded together, and then water comes along and separates them. Now, let me explain something to you. And there's two key words here. What is the term of the thing holding those two atoms together? What'd you say? Love. It is love. It's a bond of love, right? This is a bond. Now, let's be more specific. Which kind of bond? It's ionic. Why? Okay, because sodium is a metal, chloride is a nonmetal, and they can form an ion. Very good. That's where I'm going. Hold that thought. This is where I'm going. So let me ask you this. So sodium and chlorine are ionically bonded together. True or false? That is true. Water comes along, the piranha, and shreds that bond. Now, what is it called that's holding this sodium to this water? That is an IMF. So that is an interesting concept, because what have we always talked about in terms of bonds versus forces? Which ones are stronger? Bonds are stronger. Is that true in this case? No. So what does that tell me about the polarizability and the strength of the water molecule in solutions with compounds who are ionically bonded? Is it possible for the force to be stronger than the bond? Yes. So if something is soluble, how would we define it? The ability to be broken apart or dissolved. What is that truly and only dependent upon in terms of this word and this word? How is it possible? The force has to be stronger than the bond. Does that make sense? So, if the force is weaker than the bond, what does the solid not do? It does not dissolve. Potentially. It has a tie-in to that. But it all has to do with how strong this bond is. Okay? Now, here's the interesting part. Does the solubility part of this bond have anything to do with the melting point or boiling point? Not directly, but it's correlated in a way. Because the stronger this bond, do you think water can attack it as effective? No. And it should also have a higher boiling and melting point, right? All right. So that's just kind of, we're taking a silly little picture, but we're explaining how solutions work. Yes, ma'am? Not necessarily. You can make an acid do it too. Depends on what solution you're working with. Okay? Alcohol can do it. Alcohol is weaker, but it can. Water is not, I wouldn't define it as the strongest, but it's one of the most effective. Yes, sir. Of which part? All right, if we use sodium fluoride, what determines the strength of that bond? Is kind of what your question is. All right. I'll tell you this, sodium fluoride has a stronger bond than sodium chloride because fluorine is more electronegative. Okay, so it's going to hold on to that sodium, and plus it's a little smaller. So the larger the atoms get, the weaker that bond gets. And we'll talk about a little bit of that later. Okay, that's a good question. All right, so we do know this. In water, the two oxygen-hydrogen bonds. Now, let me make sure you understand this. How can we have two oxygen-hydrogen bonds? Because there are two hydrogens, right? So if I take oxygen, are there not two oxygen-hydrogen bonds? Yes. Now, it says right here that the two oxygen-hydrogen bonds, now, next word, this is important, bond. How do we know that they are bonds? What's the definition of a bond? Combines two or more elements or atoms. Okay, that's why it's a bond. Are two or more atoms combined? Yes. Okay, and then it says are polar covalent. How do I know that this thing right here is polar covalent? Oxygen is more electronegative. So you get the oxygens, the electrons spinning up here. Which side would be partially negative? Why is oxygen partially negative? It's pulling the electrons closer, so I've got partially positive ends here. Would this occur on both sides? Yes, exactly right. So really what we have, in essence, is a... Do you agree that that would be true? So what can we summarize about this? Do you agree it's two partial negatives? Because it's gaining two electrons. So that's essentially what water's doing. So from that first sentence, the two oxygen-hydrogen bonds are polar covalent. Oxygen has a higher electronegativity, and thus the electrons are more attracted to the oxygen and spend more time there. This creates a partial charge. We already know this. Here's the next part. Very interesting. This unequal charge distribution makes the molecule polar. We already knew that. Okay, the molecule is polar, and also notice the what bond angle? 105. If you don't know those, it is very critical that you begin learning them again. Bond angles are super, super important. Okay? What does? Yes, yeah. So if you go back to it, it's going to create the electron pair here and the electron pair here. It's still going to have those. No, because you remember, if you talk about domains, if you talk about oxygen, remember hybridization? All right, so oxygen technically has 6 valence electrons, right? So it has the ability to add a hydrogen. All right, so remember S, so we have one, actually this, because electron pairs take up more space. So remember, if we did the flower petal, SP, P1, P2, so it's SP3. Anytime it's an SP3, it's bent. If it's SP2, it was angular. And this is so rare that I can't think of anything off the top of my head that actually comes up to be angular. I did, but I can't remember off the top of my head which one it is. There is one that has X, and I can't remember exactly what it is, but it's got one lone pair. Oh, check. What am I doing? Hybridization is that. We're talking about the model number as well. AB2 E. No. Yeah, that was really bad. AB2E2, and this is AB2E. If you're looking at that like it's Greek letters, I need to explain it. Does everyone get that? The E is the extra pair of electrons. So water has 2 extra pair. That's why it's got E2. The B is what is bonded to it. So you've got a hydrogen and a hydrogen, so it's got 2 bonded atoms. And I cannot remember what the... Yeah, but boron never forms something like that. Because boron can always form trigonal planar, because it only needs 6. Okay, alright, so, go ahead. Go ahead and ask. Yes, sir. Yes, absolutely. It'll be the same ones from last year, but it'll be refreshing. Because honestly, everything I taught you last year will get you to be able to answer any geometry question. You got that? Say it again. Alright, so again, also notice in 105 that the 2 unshared electron pairs are hogs and require more space than shared pair. If you don't hear anything else, hear this today. This is something that I did not focus on last year because it's an advanced concept. The 2 unshared electron pairs are hogs and require more space than a shared pair. Okay? So, if it's an electron pair, does it take up more or less room than a bond? More room. Let me go back to water one more time. So, remember, in chemistry we have something called a space filling model, and if you Google it, it'll show up. So, I've got oxygen, and then I've got the electron pairs here, the electron pairs here, and then I've got the bond and the bond of the H and the H. So, if we did this in a space filling model, essentially what would happen is we would have something kind of like this, something kind of like this, and then for the 2 electron pair, would they be more or less space taking? More. So essentially, you would kind of have something like this. They would overlap. They take up more space. Yes, ma'am. He's right in a way. These 2 electrons are locked in with another atom. These 2 are locked in. So they're really going to be kind of tied in like a rope, essentially. But these 2 are free to go wherever they want to go at any point. So they're allowed to kind of escape the atom a little bit farther, which gives them more freedom to roam. And in essence, what they're going to be allowed to do, because remember, can water attach to other waters? Can water stick to water? Yes. What's going to happen is you're going to get a force between this electron pair and a hydrogen from another water molecule. So they're going out seeking and searching for more things to attract. That's why it can take up more space. These 2, the oxygen, do not want to let them go because it wants to keep those hydrogens pulled toward it. Yes, sir. Hang on. Nick, go ahead. Kinda. It would stay within the orbital of this molecule, if that makes sense. It can be found anywhere, yeah. Because remember, these things are constantly moving, so it would be in an orbital, yes. And which hybridization orbital it would be in, it's kind of above my knowledge level. Okay? All right, thus the 109.5 angle is squished to about 105 to create bent. These two unshared pair of electrons associated with the oxygen are two partial negative charges. Okay. Again, this is the important part. It just kind of shows you again the 105 of how everything is bent as well. Our properties of aqueous solutions. This is important as well. Water has many unique chemical and physical properties, fairly low molar mass, but relatively high melting and boiling points. Why do they have high melting and boiling points? Why does water have a high melting and boiling points? And it's one word, or it's one phrase. Say it again. Perfect. That's the exact answer. It has hydrogen bonds. What do we know? First of all, why are hydrogen bonds a trick verbiage? Say it again, Colby. They're not bonds. What are they? They are forces. Okay? Hydrogen bonds. But they can create stronger forces than some bonds are. So, this is why it's very important that we understand what hydrogen bonds are, because they can give us high melting and high boiling points. It expands upon freezing. Notice that is a lot larger than normal. Why is that weird? First of all, let's take freezing. First of all, what is freezing by definition? Liquid turning into a solid. If you take the the viscosity of fluid, and you take it and you turn it into a solid, what would you expect the particles to do? You would expect them to get closer, right? In terms of their velocity, what are the particles doing when they freeze? They slow down. Now, let me ask you something. Here's the hardest concept. Do you have to introduce them to a cold temperature to slow them down? No. What else can you do? What? Not no pressure. Increase the pressure. Because if I take pressure and I start pushing on something, is it going to force it closer together? Yes, and there's not much space enough for them to move around. So eventually they've got to slow down a little bit because there's not enough room for them to move. So I don't want you to think freezing is induced by being cold. You just have to basically take the molecules and get them to get closer together by any means necessary. Now, why does an increased cold temperature allow them to get closer? They're slowing down, right? Cool them down, slow them down. So why is this weird? You would expect it to get closer, but in actuality, it expands. If you take a drink and you put it in the freezer, what could it possibly do? Explode. Well, that doesn't make any sense. It's getting colder, right? It should be condensing. Well, shouldn't the can be able to hold the volume M if it gets closer? Well, why does the can explode then? The pressure of the volume pushing out on that can, the can has a fracture point, and it's going to bust if you leave it in there for long enough. So this is one of the odd properties about water, is that it actually expands as it freezes. And I know what your next question is. Why? I really don't know. But that is one of those things that I probably should know. Did I? I don't remember. I need to look that up. Okay. I need to ask Miss Huff. Maybe she can explain. Okay. It does have something to do with how the geometric solid fits together. It doesn't fit closer, it fits looser. Okay? So able to dissolve many different substances, rarely to find pure water in nature. Tap water contains dissolved substances, minerals, fluorides, and chlorine as well. Okay? I don't know of anywhere you can find it. The ground, once it has gone through the filtration levels of the aquifer. It will, and see, I don't think you can. You can make it, yeah. You can distill it. I have some. Yeah, that goofball was drinking it. It'll dehydrate you. Yeah, it'll dehydrate you. Alright, so water, the common solvent, again, hydration. Since the opposites attract, the positive ends of water are greatly attracted to the negative ions in a crystal, and while the converse is also true. So whenever the piranha water is able to come in and separate the ionic solid, they're able to take that bond and they're able to break it. okay, then that means that the positive ion is going to go towards which end of the solid? Excuse me, check. Let me start with the positive ion of the crystal is going to go to which end of the water? The negative, which would be the oxygen. I'll get to that in just a second, okay? So also conversely, the negative ion would go to the positive end of the water, which would be what? The hydrogen. Solubility. NaCl is highly soluble, while AgCl is classified as insoluble, which we will talk about later. When the hydration attractions are greater than the crystal lattice, the compound is soluble. Put a big huge star beside that whole last sentence. That is the chemistry answer of why things can be dissolved. So someone says that salt or that sugar is able to be dissolved. This is the correct chemistry answer. When the hydration attraction, so let's stop right there. First of all, what is hydration? Water. What is an attraction? How do you define attraction? But you understand an attraction, right? Okay. So when the water attraction is greater than the crystal lattice. Now we took a field trip last year. What is a crystal lattice? All right, it is. It was a field trip. No. So this is how things lock and interlock together, right? Now, that is in a 2D scale. Is there a third dimension that runs around it? Yes, absolutely. So if I could draw lines through it to make it stronger, then obviously every point where an atom attaches to a bond is the creation of the crystal lattice. So if water has the ability to come into this crystal lattice and dissolve that bond, will that thing dissolve? Yes, which makes it, quote, soluble. But what if water's hydration force is not strong enough? Then it's considered this word, insoluble. Now, how many of you want to be lawyers when you get older? Anyone? There is a lawyer's definition to insoluble, and you're going to be really mad when you hear what it is. We'll talk about that later, okay? Just keep that in the back of your mind. Now, note, their particles are charged ions. They have a full charge. Why is that different from what water has? Water is partially charged because of water. Because of what specific reason? What is the one plant fiber that's the major factor in that? Starts with a C. Cellulose. That's why whenever you eat corn and you see it on the back end, the whole entire kernel is. So let me talk about my part. Why is it different? So if I take sodium chloride, how did sodium chloride form? It's an ionic bond. Ionic bonds have to have ions, which are charges, right? But we know water is non-ionic. What is it? It's covalent, but more specifically, what's covalent? It is polar covalent. So it has these things called partial charges. What is the difference between the full ion and the partial charge? Exactly. So that's the biggest difference. There's supposed to be an R in there. So whenever we have ionic bonds, does sodium just kind of give its electron back and forth? No, it literally says, take that thing, I don't want it, but we're going to stay together just because I like hanging out with you. Okay, so chlorine has the full effect of that electron. It does not give it back. But whenever you have covalent bonds, does the hydrogen sometime get that electron back? Yes. Very little because of what difference in strengths. What strength factor is caused in there? The electronegativity factor, right? So because water is so much more electronegative, it's going to give it back sometimes, but not very often. And so that's what's going to start happening. Notice that when you pull these ions into solution, listen to that one more time. When you pull the ions into solution, what does that mean? When I take this bond and do what with it? I separate it and I surround this with water and I surround this with water. Are ions pulled into solution? Yes, that's what that means. Okay? So, this right here is probably the most emphatic picture that I need you to understand. Do you see what this looks like? I'm going to explain it, and let me show you something real quick. I know we're running out of time, but give me just 1 second. Dang it, I've already closed it. No, I didn't close it. Last year, on the exam, one of the questions that was the easiest question on this entire test was right here. Write a balanced chemical equation for the dissolution of calcium hydroxide solid in pure water. And then notice what it said. In the box below, complete the particle representation diagram that includes how many? When it says how many, what do you draw? 4. Don't draw 3, don't draw 5, draw 4. Water molecules with proper orientation around the calcium 2+ ion. Do you think that you should have earned that point? Here's the important part that some of you may not know yet. What in the heck does that mean? What side of the water should have faced the calcium? The oxygen end. Now, what side of this Mickey Mouse looking structure is the oxygen? The big one. So do you agree that it should have kind of sat something like this? This was seriously a part of the question. Should you have earned that? Yes, you should have. Okay? All right, we'll finish this up tomorrow.